Alright, welcome back. In the last video, we ended by talking about how to measure atmospheric pressure using a barometer. What we're going to look at now is we're going to look at how to measure the gauge pressure using a tool called a manometer. And specifically, this is an open tube manometer. There are other ways to measure pressure as well, but these are the two that you're going to look at just so you get a little bit familiar with them. Here's what that looks like. Imagine that you have some gas contained in a volume like this. Okay, so we have a gas at some pressure. I'll call it PG. It's a little too narrow. Not that it really matters. Okay. Oh, I guess that should be open. So I'm sorry, I screwed that drawing up. Imagine that that's open. Now, the gas at some pressure, there's a little opening that goes to a tube that would be open to the atmosphere, but what we've done is we've put some liquid in this tube. Okay. Now, at this level, we must have the atmospheric pressure because this is where the liquid stops going up because it is exposed to, this is supposed to be exposed to the atmosphere. So this should be atmospheric pressure right here because this is open, this is in contact with the atmosphere, this is atmospheric pressure here. This must be at the gas pressure. Okay, the gas pressure in here, which we would call the gauge pressure. If we just want to know what's the pressure just due to this gas, we could find that here because again, we have an interface where we have basically the meeting point between where the gas is and where this liquid is. So again, we focus on this height h, which is the difference in height between the PG level and the P0 level. We have atmospheric pressure at the top of the tube. We have the gauge pressure, the pressure not due to the atmospheric pressure. At the gas/liquid interface. And therefore, P gauge is equal to PG, and that's given by the formula rho GH. Basically, this pressure right here, the amount of pressure gotten down to the amount of pressure that would be in the liquid right here must be equal to the pressure of this gas right here, which is the gauge pressure. Okay, so again, we see that we can measure the gauge pressure using this idea of pressure decreasing or increasing as depth increases, rho GH. What we're going to take a look at now are a couple of principles, not necessarily dealing with pressure and depth, but just a couple other neat fluids topics. And the first is Pascal's principle. And I will admit, this is actually, I've never seen a question on the AP exam or in the AP book that has to deal with Pascal's principle, but it's something useful and I feel like you should know about it. Pascal's principle says the following. Changing the pressure P in one part of a fluid changes the pressure everywhere else as well. And this is the principle behind hydraulic systems. Okay, there you go. So, I'm going to draw another picture. Let's say that we have this sort of setup. Okay, we're going to draw a picture of a hydraulic system. And in this hydraulic system, so we have a tube that has two different basically cross-sectional areas. Let's say that we have two pistons. We're going to call this piston number 1 of area 1. And we have another piston over here. Okay, so basically you can think of it just kind of like a rubber plunger or something that's in here. We have piston 2 of area 2, and you can clearly see that A2 is bigger than A1. And the rest of this is filled with some sort of incompressible fluid. Well, the idea behind a hydraulic system is this. Let's say that we push down on piston 1 with a force F1. So we apply F1 to piston 1. And by applying a force, okay, by pressing on this fluid, we are trying, if it was a gas, it would compress. But remember, fluids are incompressible. So that by applying this force, what we must be doing, since a force is equal to pressure times area, we're applying more pressure to this fluid. So applying F1 to piston 1, it creates a change in pressure in all parts of the fluid. Even over here on piston number 2. If we increase the pressure on piston 2, then that means that there must be an upward force supporting piston 2, and that upward force just increased. But the cool thing is that force is not the same. Since delta P is the same everywhere, we have the following. Delta P for piston 1 equals delta P for piston 2. And since we're talking about differences in pressure, that means that we have, again, we're talking about pressure, that means that we have this relationship between the force and the area of the pistons. F1 over A1 must equal F2 over A2. Let's do some rearrangement. If I solve for F2, that means I move A2 to the other side. I get that F2 must be equal to A2 over A1 times F1. Since A2 is greater than A1, that means A2 over A1 would give you a number greater than 1. That means that F2 is some number greater than 1 times F1. In other words, F2 is greater than F1. In other words, the output force, remember we push down on F1, and we get or the input force was us pushing down on piston 1 with F1. The output force, the force on piston 2, is bigger. So this is really neat. We could either support something that's very heavy with a very light or a very small input force, or we could lift something that's very heavy with maybe just a little bit more added force in there. So this seems really cool. We can pick up these very, very large objects. But there's a catch. There's always a catch. Okay? Everything I just said is true. If we are assuming that the fluid is incompressible, as we always do, let's say we want to raise, we push piston 1 down to raise piston 2 up. Pushing piston 1 down by, let's say, a distance of d, should increase, or should the level of piston 2. If we do this, piston 1, as it moves down, it's got a certain area here, that's the area of this tube that piston 1 is stuck in, and it moves down a distance d. It therefore displaces a volume of fluid V1 equals A1 times D1, okay? Because if we move it down a certain distance, it's got this area. We've got to push that chunk, essentially, of the area multiplied by the distance of fluid over this way. If we're going to move this one down through a certain volume, this has got to move up through a certain volume. Since V1 must equal V2, then V2 equals and V2 equals A2 D2. Then we have A1 D1 equals A2 D2. If we solve for the distance that the second piston moves when we push piston 1 down, we end up with A1 over A2 D1. And since A1, or I should say since A2 is greater than A1, then that means that D1 is greater than D2. So here's the drawback. You need to move. It's easier to support something, or you don't have to use as much force to push up piston 2 if you're pushing on piston 1. But you need to move piston 1 farther than piston 2 moves. Okay? Piston 1 will always move at a greater amount than piston 2 does, because those volumes of the air that, or the liquid that is the fluid that is moved, have to be equal. Another neat thing, if we're talking about a force moving piston 2 through this, that means that if there's a force moving something through some displacement, that means the work done on piston 2 must be equal to the force on 2 times the distance that 2, or the displacement that 2 moves through, I guess times cosine theta 2, but we know that the force and the displacement are in the same direction, so we can get rid of that. Well, F2, we just solved for that. F2 was equal to A2 over A1 times F1. D2, we just solved for that, A1 over A2 times D1. I have an A on the bottom, A on top, or A1 on bottom, A1 on top, A2 up on top, A2 on the bottom. Those will cancel out. I get F1 D1, which is equal to the work done by piston 1. So interestingly, the work done by each piston is the same. So what we're really going for here is that the work done in moving these pistons in this hydraulic system is equal, it doesn't depend on whether you're moving piston 1 or piston 2. By moving F1, because the area is smaller, you can use a smaller force to generate a bigger output force, but you're going to need to move piston 1 through a greater distance in order to move piston 2 even a small distance. So there's a trade-off here, but that's how hydraulic systems work. There are ways around that, so this is essentially how we pick up cars, like in a car auto body shop, there's a hydraulic system there. There are some ways around this, but this is basically how Pascal's principle works. Again, never seen it on the AP test, but I think it's a good thing to know and just understand how fluids and pressures work like this. Now we're going to talk about buoyant force, and this is one of the big topics in this unit. We're probably going to have to cut this off about halfway through, but that's fine. So let's say that we have a volume of liquid in a still pool. So in other words, no acceleration, forces are balanced. Free body diagram for that might look like this. Here's our volume of liquid. Up is positive. If the forces are balanced, we know that the liquid is going to have a gravitational force downward on it. There must be some force pointing upward. That's going to be referred to as the buoyant force, okay, FB. Our net force equation would look like this. F net y equals FB minus FG equals MAY. If that's 0, then I get that the buoyant force must be equal to Fg, where Fg we know is equal to mg, where m is the mass of the liquid. But remember, we don't really talk about mass much in this unit. We're going to talk about density and volume instead. I know that density equals mass over volume, so I can rewrite this as the following. The buoyant force is equal to the density of the liquid multiplied by the volume of the liquid times g. So just to summarize, an upward force, which is known as the buoyant force, balances the downward Fg. And what this buoyant force really arises from is the pressure differential the pressure difference between the bottom and top of the volume of liquid. Okay, that's where it really comes from. Because the pressure, as we saw before, on the bottom of the liquid volume is greater than the pressure at the top of the liquid volume, we end up getting this pressure differential, and that creates a force upward, and that force is known as the buoyant force. Now we're going to do something a little strange. We're going to replace the volume of the liquid with an object, object of the same shape and size. And the interesting thing is, because the buoyant force is about the pressure difference between the bottom and the top of this volume, the buoyant force shouldn't change. Because the object's the exact same size, the pressure in the water at the bottom and top points should be exactly the same. So buoyant force shouldn't change because the pressure difference is based on the size and the shape of the object. And all we've done is we've changed out what type of object is there. Before it was a whole bunch of water, or a whole bunch of liquid, I should say. Now it's just some object, which isn't affected. So we're going to draw a free body diagram, and it's going to look pretty much the same, but this time we're not going to assume the acceleration is 0. So we're going to have, here's our object, buoyant force upward, force of gravity downward, F net y equals FB minus FG equals MAY. The buoyant force, as we saw before, was equal to the density of the liquid times the volume of the liquid times G. And we're going to do minus mass of the object, because now the force of gravity is for the object, so mass of the object times G equals the mass of the object, AY. We're going to run through a few more algebraic steps. I'm going to take this mass of the object and change it like thus. We're going to change, and since we're talking about fluids, we want to change this to the density, just so we can compare all densities of the object times the volume of the object times G equals M object AY. And finally, we're just going to realize or remember that when we changed this out from a volume of liquid to an object, we didn't change the volume. So actually, this V liquid term that we have here must be equal to V object. So if those two things are equal, then watch what I'm going to do here. I'm going to do the, let's see here, the volume of the liquid times G. I'm going to change this to volume liquid because it's the same thing, times G times the density of the liquid minus the density of the object must be equal to the mass of the object times AY. And this leads to some interesting scenarios. If, and it all has to do with this argument right here inside this parentheses, if the density of the liquid is equal to the density of the object, then the object stays submerged. I should say, we're assuming that we have something, it's well below the surface. We're dealing with something that is complete, like an object that's completely submerged with water. Well, what happens if the density of the liquid is greater than the density of the object? Okay? Remember, if the density of the liquid was equal to the density of the object, then this would be 0, and we'd get no acceleration. What happens if this is greater than this? This becomes a positive number. Volume and G are going to be positive. That means the acceleration is positive. We said upwards was the positive direction. So if the density of the liquid is greater than the density of the object, then the object accelerates upward until it's floating. We're going to put an asterisk by that. We're going to come back to that in the next video. If the density of the liquid is less than the density of the object, then this would be a negative inside this parentheses. We'd get negative acceleration. Object accelerates downward. Or in other words, it sinks. So to sum everything up, if the density of the object is the same as the density of the liquid it is in, the object will just be submerged. It'll just kind of, I wouldn't really call it floating because it's not on the surface. It just kind of hovers. It's suspended. If the density of the liquid is greater than the density of the object, then that means that the liquid's more dense. The object will end up floating. And there's something we're going to come back to with that. If the density of the liquid is less than the density of the object's more dense, the object ends up sinking. So sinking and floating, or just being suspended, depends on basically the relative densities of the liquid and of the object. We'll come back to this in the next video. We'll finish buoyant force up, and then we'll talk a little bit about volume flow rate and the equation of continuity, which are topics when we're dealing not with just static fluids, but flowing fluids.